y'all. Junior back with y'all. Junior back. There we go. That should be better. Junior back with some more uh, thermodynamics. So what we'll do is continue reading from where we left off last time uh, with 6.4, the Maxwell speed distribution, which is something I know nothing about. We'll see what this is talking about. For our next application of Boltzmann factors, I'd like to take a detailed look at the motion of molecules in an ideal gas. We already know from the equipartition theorem. Let's remind ourselves what that is. Okay, that's right. Equipartition theorem. That is basically that each degree of freedom of each quadratic degree of freedom of a gas is so basically it's U equals N F over 2 KT. Oh, and it's big N. There's equation 1.23. That's thermal. Euthermal is NF 1/2 or F over 2 KT. That the root mean square speed of the molecules is given by the formula. So I'm not sure how we know that. Then V R M S equals square root 3 KT over M. Suppose if U equals 1/2 MV squared equals N over 2 KT. Let's say V squared equals N F K T over M. We could say V equals square root of, and if we take N to be 1, F K T over M. And we have 3 degrees of freedom, length, width, and height. VRMS equals square root of 3 KT over M. So that seems to be how they get that from the equipartition theorem in the basic formula for velocity. But this is sort of an average. So each individual particle, some of the molecules will be moving faster than this, others slower. In practice, we might want to know exactly how many molecules are moving at any given speed. Equivalently, let's ask what is the probability of some particle, of some particular molecule moving at a given speed. Technically, since the probability that a molecule is moving at any given speed, v is 0. Since speed can vary continuously, there are infinitely many possible speeds, and therefore each of them has infinitesimal probability, which is essentially the same as 0. However, some speeds are less probable than others, and we can still represent the relative probabilities of various speeds by a graph, which turns out to look like figure 611. A graph of the relative probabilities for a gas molecule to have various speeds. More precisely, the vertical scale is defined so that the area under the graph within any interval equals the probability of the molecule having a speed in that interval. Right? The most probable speed is where the graph is highest, and other speeds are less probable in proportion to the height of the graph. Furthermore, if we normalize the graph, that is, adjust the vertical scale in the right way, it has a more precise interpretation. The area under the graph between any two speeds, v1 and v2, equals the probability that the molecule speed is between v1 and v2. So that seems sensible. dv is the height of the graph. That's an odd thing to call the height of the graph. If the interval between v1 and v2 is infinitesimal, then dv doesn't change significantly within the interval, and we can write simply the function dv is called the distribution function. Okay, now they're explaining what dv is. Its actual value at any point is isn't very meaningful by itself. Instead, dv is a function whose purpose in life hold up, to be integrated. To turn dv into a probability, you must integrate over some interval of v's. So this is like the probability distribution in quantum mechanics. Or if the interval is small, just multiply by the width of the interval. So that's something to keep in mind. Integrate v1 to v2 or change in v if small. The function dv itself doesn't even have the right units, namely none, for a probability. Instead, it has units of 1 over v or meters per second negative 1. Now that we know how to interpret the answer, I like to derive a formula for the function dv. The most important ingredient is the derivative of the Boltzmann factor. And remind myself what the Boltzmann factor is. That's here it is there. Right, we have that. Another important element is the fact that space is three-dimensional, which implies that for any given speed, there are many possible velocity vectors. In fact, we can write the function dv schematically as dv is proportional to the probability of a molecule having velocity v and the number of vectors v corresponding to speed v. There's also a constant of proportionality, which we'll worry about later. The first factor in equation 6.44 is just the Boltzmann factor. Each velocity vector corresponds to a distinct molecular state, and the probability of a molecule being in any given state S is proportional to the Boltzmann factor. In this case, energy is just the translational kinetic energy, 1/2 mv squared, where v equals the absolute value of v. So probability of a molecules having velocity v is proportional to E mv squared over 2 kt. I've neglected many variables besides velocity that might affect the state of the molecule, such as its position in space or its internal motion. This simplification is valid for an ideal gas, where the translational motion is independent of all other variables. Equation 6.45 says that the most likely velocity vector for a molecule in an ideal gas is 0. Given what we know about Boltzmann factors, this result should hardly be surprising, as low energy states are always more probable than high energy states for any system at finite temperatures. However, the most likely velocity vector does not correspond to the most likely speed, because for some speeds there are more distinct velocity vectors than for others. Not sure what that means. So let us turn to the second factor in 6.44, the number of vectors corresponding to speed v. To evaluate this factor, imagine a three-dimensional velocity space in which each point represents a velocity vector, right? We're talking about the sphere again. It's like with momentum. The larger v is, the bigger the sphere and the more possible velocity vectors there are. So I claim that the second factor in equation 6.44 is the surface area of a sphere in velocity space. That makes sense. So don't rewrite this down. That's what they mean by the number of velocity vectors corresponding to a speed v. So if we have v, x, y, and z, the and we pick one vector going at this speed, you can have v equals square root of vx squared plus vy squared plus vz squared, and all four pi area of the sphere will equate to that same v if you pick the proper values of vx, vy, and vz. So on the x-axis, it will be vx equals v, but where I drew the arrow there, it might be some combination of vx, vy, and vz that'll still end up with v. And here, we have proportional to e negative m v squared over 2. Put a b there. This is proportional to 4 pi v squared. Putting this degeneracy factor together with the Boltzmann factor, we obtained dv equals c, constant of integration, e negative m v squared b over 2 and 4 pi v squared. So this seems to be something to convert. Yeah, I guess this one is going to stay like that. Where c is a constant of proportionality. To determine c, note that the total probability of finding a molecule at some speed must be 1. It makes sense, like normalization. There's no negative speed, so that's why it goes from 0 to infinity. Four pi is c out, the v squared is still there. The e negative mv squared over 2b is still there. And here we go with this change in variables thing again. So x squared equals m v squared b over 2, since v is squared. X equals square root m v squared b over 2 equals square root m b over 2 v. Dx equals square root m b over 2 dv. So 1 equals c 4 pi 0 infinity e negative x squared and dx over square root of m b over 2. I'm not sure why their change in variable is different. Oh, I see. Off my v squared here. So v squared equals x squared 2x squared over mb. So this equals c 4 pi integral 0 to infinity 2x squared over mb and e negative x squared dx over square root of b over 2. If this adds up to the same, so what we would have is c 4 pi and 2 over mb and 2 over mb 1/2 integral 0 to infinity x squared e negative x squared dx. And this does in fact equal c 4 pi 2 over mb 3 over 2 integral 0 to infinity x squared e negative x squared dx. So now we have to get rid of all the x's, all the v's and make them x's. Like a pure Gaussian e to the negative x squared, the function x squared e to the x squared cannot be anti-differentiated in terms of elementary functions. Again, however, there are tricks explained in Appendix B for evaluating a definite integral from 0 to infinity. In this case, the answer is square root of pi over 16. So no x is square root of pi. 1x is square root of pi over 4. 2x squared is square root of pi over, 1x is square root of pi over 2, 2x square root of pi over 4, and so forth. Okay, so this all still equals 1. B equals m b over 2, b over 2, pi 3 over 2 equals m b over 2 pi 3 over 2. Right, so that's the same thing they have. dv equals, we'll also plug this in, this normalized to 1. Right, that's equation 6.50. So as a note, hopefully we don't have to do Gaussians on the exam, but Gaussian is square root of pi, x Gaussian, square root of pi over 2, x squared Gaussian, square root of pi over 4. This is from 0 to infinity. The result is called the Maxwell distribution after James Clerk Maxwell for the speeds of molecules in an ideal gas. It's a complicated formula, but I hope you won't find it hard to remember the important parts. The Boltzmann factor, involving the translational kinetic energy, and the geometric factor of the surface area of the sphere velocity space. Figure 613 shows another plot of the Maxwell distribution at very small v, right? So it's parabolic on the left and dies exponentially on the right. This actually reminds me of, so one of the experiments in a modern lab is a positronium experiment where I didn't do this experiment, but I saw helped some of the students with it and saw how they saw their presentation. And basically they put some, I believe sodium 22 in a vacuum chamber uh, and fill the chamber with nitrogen to capture the positonium that binds with basically a positron bonding with an electron and then it annihilating after a short period of time, if I recall. And the distribution looks like this. It's sort of a Gaussian on the left side, which is like parabolic, and exponential on the right. So it seems pretty interesting that the Maxwell speed distribution matches uh, the output of the energy of a positonium capture. So I'm pretty sure there's something to that correlation. At very small v, the Boltzmann factor is approximately 1, so the curve is a parabola. And in particular, the distribution goes to 0 at v equals 0. This result does not contradict the fact that 0 is the most likely velocity vector because now we're talking about speeds. And there are simply too few velocity vectors corresponding to very small speeds. Meanwhile, the Maxwell distribution also goes to 0 at very high speeds, much greater than kt over m square root, because of the exponential fall off of the Boltzmann factor. In between v0 and v infinity, the Maxwell distribution rises and falls by setting the derivative of the equation 6.50 to 0. You can show that the maximum value of dv occurs at vmax. Right? As you'd expect, the peak shifts to the right as temperature increases. Makes sense? The most likely speed is not the same as the RMS speed. Referring to equation 6.41, we see that the RMS speed is the greater of the two, by about 22%. The average speed is different still. To compute it, add up all possible speeds, weighted by their probabilities. I remember the day professor went over this in class. In this equation, I'm imagining the various speeds to be discretely placed, separated by dv. If you turn on the sum to an integral and evaluate it, you get we have this v hold up v max, v this, and then vrms in this order. As an example, consider the nitrogen molecules in air at room temperature. You can easily calculate the most probable speed, which turns out to be 422 meters per second at 300 Kelvin. But some of the molecules are moving much faster than this, while others are moving much slower. What is the probability that a particular molecule is moving faster than 1000 meters per second? First, let's make a graphical estimate. 1000 meters per second exceeds Vmax by a factor of 2.37. Looking at figure 613, you can see that at this point, the Maxwell distribution is rapidly dying out, but not yet dead. So I'll take Vmax and double it, and then do a little bit. We're about right there. Area under the graph beyond 6.37, Vmax looks like only 1 or 2% of the total area under the graph. Quantitatively, the probability is given by the integral of the Maxwell distribution from 1000 meters per second to infinity. Just this. We integrate this to get the most probable speed. With this non-trivial lower limit, the integral cannot be carried out analytically. The best option is to do it numerically by calculator or computer. You could go ahead and plug in numbers at this point and start your computer to work in units of ms, but it's much cleaner to first change variables to x equals that. Just as in equation 6.49, the integral then becomes, well, the lower limit is the value of x when v equals 1000 meters per second. That is x min equals 1000 meters per second divided by 422 meters per second of 2.37. Now it's easy to type the integral into a computer. I did so and got an answer of 0.0105 with the probability. Only about 1% of nitrogen molecules are moving faster than 1000 meters per second. That seems pretty clear. And I have to do 638. So 638 is at room temperature where fraction of nitrogen molecules in the air are moving less than 300 meters per second. It's easy enough to do. For about 37 minutes. I think I have time to do this problem here. So I'll change the text to problem 6.38 and 6.38, 6.41. I'll do 6.3 for now. Technically, I can just grab the equation they gave me here. Want it to be smooth with it, but I'll go ahead and derive the thing for some practice. So we have v equals mv over 2 pi 3 over 2 4 pi v squared e negative mv squared over squared v over 2 v equals 1 over kt. So we want to integral from 0 to 300 meters per second of mv over 2 pi 3 over 2 4 pi v squared e to negative mv squared b over 2 dv. So x squared equals mv squared b over 2. X equals square root mv over 2 v dx equals square root of mv over 2 dv. dv equals 2 over mv square root dx. And v squared equals x squared 2 over v. We have integral from 0 to 300 meters per second. mb over 2 pi v over 2 4 pi 2x squared over mb e negative x squared and 2 over mb x squared dx. May have done something incorrectly here, so I'm glad I'm practicing. Let's see here. So x equals v 2 v over 2. That seems right. I have my 4 pi b over 2 pi to 3 over 2 v squared e to the negative mv squared v over 2 dv. That seems right. And that's the difference. They're saying x is v over v max. I think this is the first time this book didn't actually put in enough steps. Right. Well, I'm going to have to look at this conversion later. If I hit the say to do the problem, I could just use the equation we have here, which is x equals 4 over square root of pi integral x1, x2, x squared e negative x squared dx. I guess this should be probability. Pi 2 x squared dx. So in this case, we have 4 over square root of pi, 0 to x max I see. So what I have to do is get the v first. Which we have here. The average equals square root of 8k T over pi m, which for which for nitrogen equals 422 meters per second. And that's from the text page 245. So we want uh, 1 V over V max, which is 300 divided by 422. So that equals 0.71. So that means the probability is going to go 4 over square root of pi 0 to 0.71 x squared e to the negative x squared dx. All right, so he typed this integral into a computer, so looks like that's what we have to do since it's not a from 0 to infinity. Let's put this in and see what we get. All right, so I get 0.2000732. Seems reasonable. For my visual uh, graph, I get this. This is the area underneath this curve here. Right. So 20%. So 20% of the gas is going less than 300 meters per second. Uh, Perhaps I don't need to figure out how to do that conversion since we have the equation like so. But let me come back another day and look at it. For the time being, I'll just stick with the fact that we have the equation. Just have the probability, have the average uh, speed, just have to get the mass for any particular species, and Oh, and I have this wrong, by the way. V min over V. Uh, so that's the probability by which it exceeds the most probable. Peak is relevant because it's the peak with the epsilon that came from this. And this is coming from directly from equation 6.55. Right, so you have to make sure I have these on my formula sheet. All right, y'all. Oh, and by the way, so I was writing here. So we have V min divided by V average. V average is this, which we got from the book, page 245. That gives us the fraction we need, 0 to 0.71 to the left of the most probable. And there we go. So I'll see y'all tomorrow on my other channel for some quantum mechanics. We're working on that to do that tomorrow. It's pretty complicated. So I may even do a background video here first, since the background is a bit more complicated, and then go for the overview there. I'll see how it works. Thank you all for joining. Like, subscribe if you haven't. Have a good one.